Yeah, so we're going to talk about megasystems and system-specific interpreters. So, here's the whole thing in one slide, right? So the problem is that we've got these big code bases, Linux, Chrome, blah, 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 that are these huge systems, they're terrible to work with, they're hard to build, especially for sort of hobbyist programmers, taking 2 or 3 CS classes in undergrad, and they're asking, what's going on my machine, right? So the solution we're proposing is to write, system-specific interpreters that let you easily execute just parts of these systems in isolation. All right, so just to drive home the point, these systems are huge. We're talking about millions of lines of code, yet we use them every day, all the time. Okay, and here's some fun screenshots showing sort of how hard to build these things are, right? Like there's a whole WikiHow article about how to build the kernel. For Chromium, it depends on if you're a Google employee, how you're supposed to build it. And if you're trying to build on something other than Linux, like LibreOffice on Windows, you don't get build instructions, you get tips and tricks. Right, so these are and even if you can figure out how to build it, it's slow, right? I think that's kind of undeniable for a lot of these systems, at least for the first build. And once you build it, it's also hard to run them, right? So if you're really just interested in this one, little part of the Linux kernel or something, you got to figure out how to reach that from the whole system. And you may not even have the right hardware to run it. It's hard to trace them once you get the part you want running, right? So if it's an operating system and it doesn't boot, how do you even trace it? You got to plug in the JTAG or something. And even on sort of user level programs, there's a huge number of concurrent things happening. And so how to filter down to the behavior you're most interested in. So in some sense, I think these are sort of like the opposite of live programming. I think these were sort of mentioned as like zombie programs earlier in the day, right? And I think so they really fail all of these conditions that we would love to have from our live programming systems. And instead, we would want to be able to just start running and tracing the code in sort of a simulated environment as soon as possible. So that's what we propose to do, right? So we propose to, and we do write some of these system-specific interpreters, which let you just run an individual file in these huge systems directly. It gives you a GDB-style REPL interface to those things, and it should come with some little lightweight mocks of the rest of the system for when you call out. And essentially, the idea here is to treat the rest of the system as describing a domain-specific language for this module, which is kind of a nice sort of known way of thinking about these big systems. And as a nice sort of side effect, once you do this, what we found out is we basically just got a debugger for sort of incomplete C code that you can use in a lot of scenarios here. So 2 major challenges before we go on to the demo to talk about. One is something you may be familiar with, that parsing incomplete C code is ambiguous, right? So if you don't if you don't have all the dependencies, you can't even accurately parse it. And especially if it's not written yet, you definitely can't necessarily accurately parse it. So the solution we have right now is to do this sort of parse on demand thing, where we have sort of really compositional parsers, and you don't even parse a line of code until you're about to run it, until the user actually asks you to run it. So then you can sort of, if there's a syntax error or something you don't understand up here in the file, if you never get there, it's not a problem. In the future, it would be cool to use the tidy parse sort of stuff that we're going to hear about next, I think. Right, and then the other major problem I'll talk about is, this individual file you have clearly is going to call out to the broader megasystem. So what do you do in that case? And what we found is there are sort of 2 interlocking solutions here. One is, you just treat those values you get back from the rest of the system as sort of opaque values and pass those around. And for a lot of the time, the property you're interested in doesn't actually use those values, so it becomes okay. And then when it does, there's a ability to add some lightweight mocks into the system for the broader megasystem. So let's do this demo here. Okay, cool. That got slid around. So this is a little web version of a prototype system here. So I can set up the basic example here. So this is a little C program here that's incomplete. We haven't implemented this foo function, and we haven't, written this foobar that we need. So this is an example of something that wouldn't even parse. And then we have a little basic system-specific interpreter using our framework here. So it's got a little REPL down here. And so we can run it. And then off on the side here, we can, execute, main. Execute the main function. And then we see, we could have done breakpoints, but it's a little easier this way. If it's a concrete value, it'll just do the concrete computation. If it's calling to a function, you don't know what the function returns. It just returns an opaque value. That's this opaque value here. And then when you get an opaque value, you can ask it, why is this opaque, right? And then it'll trace it back and say, it was opaque because you called x equals foo on line 10, right? So it'll sort of track that through the execution. And in this case, like it guessed X is true, I guess. So it went down this path and it didn't even need to worry about this code at all. So like if there's code that's wrong, as long as you don't actually try to execute it, you won't run into a problem, which is, it's better than just failing immediately. And so now a little bit of a more involved demo is this is what I originally sort of wrote the system for, was I was writing a little driver or a little operating system for like a Raspberry Pi or something. And, in the course of debugging, I wanted to know, like some ground truth about what should I be doing to the hardware to get it to do what I want. And I realized Linux has like a driver for this hardware device, but like I don't want to build it and trace all this nonsense, right? I just want to go like look at this driver, but there's a whole bunch of stuff going on. So what it turns out is that you can write a little SSI, and that will be fixed in a second. Yeah, there we go. And like this is what the SSI sort of looks like for this file, and then that'll let you say which device you're simulating. I can tell it to, what this is telling it is to like print out every time I try to write to device memory, and then I can run the sort of initialization method, and that'll tell me exactly sort of what values were being written out to the device, and then I can sort of compare that and make sure that matches with my own understanding of what the driver is supposed to do. Cool. So that's the talk and the demo. I'm happy to take any questions or anything like that. Back to or maybe I'll stay on the whatever. Thoughts, welcome.
Yeah, you can use it too. Yeah, I'm ready.
Okay, thanks, Matt. We had a question here.
Yes. Does this mean that you need to do an awful lot of work for the specific code base you're in? So say if it's Chrome, does that mean you need to have like a Chrome expert on hand to tell you, okay, well, these are the different APIs that this uses, and you'll have to mock this up, you'll have to mock this up.
Yeah, so
it's a quite high cost for an individual.
Yeah, I think that's a great question. I mean, I think two parts here are that, one, you don't actually have to sort of mock as much as you might imagine, because it turns out like you're maybe only, like here there's a bunch of other stuff going on with locks and whatnot that, we just don't really care about for the question we're trying to answer. And so the sort of opaque values thing lets you just ignore all of that. So you only kind of have to mock the parts that directly impact what you care about. But you still do have to mock those, and it would be nice to have maybe an expert. I do also think that this is a nice tool to use while you're learning a system yourself. So I think like as you like work on a big code base, just as a human being, right? You go through and you sort of do this mentally. You make a model of what the broader system is doing. And I think in some sense what this is telling you to do is you can like mechanize that model and actually run code against that model instead of just having it in your head. So does that answer the question broadly? Okay. Happy to do follow-ups too.
We have time for one more question.
Okay, thanks for the nice talk. I was wondering if, how would you go about modeling certain device-specific aspects, maybe using an emulator or a microkernel or something, so that you don't have, maybe if you're developing for Raspberry Pi or something like this, could you do this in the system you're describing?
Yeah, so I didn't show much of it, but basically the way these mocks work right now is it's just sort of Python code that you just hook into, and you just say, when the C code calls this function or whatever, call this Python code. And this is a very early prototype sort of thing, so there's some internals peeking through, but broadly you can think about, you just write these mocks in any kind of Python code, so you could have Python code simulating whatever aspect of the hardware you're interested in. Does that make sense?
Yeah, very interesting. Thank you very much.
Cool, thanks.
Okay, thanks again, Matt.
All right, thanks very much.